Hello everyone. Thank you for joining my video. Today I'm going to discuss and review about distributed machine learning and parameter server based on the research paper Scaling Distributed Machine Learning with the Parameter Server by Mooley and his team. So before move on to the further slides, I'd like to explain what are the topics that I'm going to discuss today. First of all, I'll explain you the background of the parameter servers and distributed machine learning. Then I'll explain some related works other companies done about this. Then I'll explain the third generation parameter server and what are the other generations we had before. Finally, after that, I'll explain some benefits of the parameter server and system architecture of the parameter server and how the parameter server use these key value pairs and range push and range pull function. Then asynchronous task and dependencies of the parameter server. Then the implementation of the parameter server and how the parameter server used vector clocks to increase the accuracy of the implementation and what kind of messages the parameter server pass in which the servers and clients. Then the replication and consistency of the parameter server and how the management done in this parameter server. Then finally I'll show you what are the references I use to make this video and more learning materials for you guys. Okay, in the background, sorry, in machine learning and deep learning, distributed optimization is a prerequisite because the single machine cannot solve the current rapid growth of the data and parameters. Okay, I'll explain that with an example. Before go to the example, I should mention here, I'll use some of the pictures and diagrams from this research paper and Mooley used in his presentation and some of the pictures from other links which I'm going to mention in the reference page. Okay, I think everyone has seen this before. As an example, if you want to book a flight, I'll just query in the Google like book a flight. Then, other than the result I need, on the top of the page, there's another link, which is an ad posted by Google. That means some of other companies has paid to Google to show this ad to the customers of Google. So the thing is, if I click this link, the Google will get money from that company. But not all the ads are interest to everybody. That means I may not click this ad if I'm not interested about that ad. If you check this graph here, you can see that the annual revenue and the ad click presentation has increased rapidly over past years. But the very important observation in this graph should be the training data size, which is around 700 terabytes. Actually, this is doubling year by year. If you compare 2010 to 2011, it has almost doubled. 2011 to 2012, it is doubled again. Likewise. So in 2008, right now, it should be around at least 1 petabyte of this training data size. This is how this machine learning algorithm works. As I explained, in reality, the number of training data may reach 1 terabyte to 1 gigabyte, and the parameters during training may reach 10 to the power 9 to 10 to the power 12. And often the parameters of these models need to be frequently accessed by all worker nodes, which brings many problems and many challenges. As example, accessing this huge number of parameters requires a lot of bandwidth support. Many machine learning algorithms are continuous, and the next iteration can be performed only after the last iteration is computed. That means after all workers are completed. If the latency between machines is large, this leads to performance loss. In distributed system, fault tolerance is essential. In many cases, the algorithm is deployed to the cloud environment because these are in the all over the world. So we cannot keep this in one single machine. In this environment, the machine is not reliable. This can have failures all the time, and the job is also likely to be crashed all the time. So now let's discuss some of the related works done by other people. Many large companies have doing a lot of experiments about this. As examples, Amazon, Baidu, Facebook, Google, Microsoft, and Yahoo actively participate to research about this field. There's also some open source projects such as Yahoo LDA, Petum, and GraphLab. Okay, in conclusion about these related works, if we compare to the other algorithms which are famous, parameter server offer the greatest degree of flexibility in consistency, and it's the only system offering continuous fault tolerance. You can see in that large row is the parameter server. In the consistency is in the middle column, and the fault tolerance is the last column. So if I move on to the next slide, I'm gonna talk about the parameter server generations. So in the first generation parameter servers, first generation parameter servers are lack of flexibility and performance. It is only use the memcached key value pair storage as a synchronization mechanism. By improving this mechanism, Yahoo LDA adds a dedicated server that provides user-defined update operations like set, get, and update. Then the second generation parameter servers improved the Yahoo LDA with the bounded delay model, but further limited the worker threading model. Okay, then the third generation parameter server can solve these all limitations. Now let's compare the differences between the parameter server and the general distributed system. A common distributed system usually each iteration is forced to synchronize. That means they should synchronize after after each iterations. Usually, if the nodes around 12, around 1000, this perform very well, very fast. But if the scale is large, such as memcache to force synchronize iterations, it can be very slow. It performs very slowly. These are some famous algorithms. Mahot is based on Hadoop, and MLI is based on Spark. And both of them use a framework of iterative MapReduce. They can maintain the state between iterations. And the execution strategy is also more optimized. However, because of the method use synchronized iteration communication, it is very easy to reduce the overall performance because the low performance of individual machines. So if you see this picture, you can see that machine 2 is very slow in the first iteration, but it is compared to other computers, it is fast in the second iterations. So in this case, in synchronous execution, all other machines, in this case machine 1 and the machine 3, has to wait until machine 2 finish. That is a waste of time in the machine 1 and machine 3. In the other case, after the first iteration they finish the communication, then they start the second iteration. In here, the machine 2 has performed their work fast, and still machine 1 and machine 3 is doing. So the machine 2 has to wait until machine 1 and machine 3 finish. So that is a waste of time in the computers. So to solve this problem, the GraphLab use graphical abstraction of asynchronous dispatch communication. However, it is lacks elasticity scalability based on MapReduce, and it uses snapshot for recovery, both of which hinder the scalability. The parameter server takes advantage of GraphLab's asynchronous mechanism and solve its disadvantage of scalability. If you look at this animation, we can clearly see that machine 1, after complete the first iteration, it doesn't need to be wait for the other machine to finish their work to communicate. They can just send the message to the other machines and go for the second iterations. Okay, after talking about these shortcomings of the distributed system, let's focus the 5 key features of the parameter servers. Okay, the first one is efficient communication. Since it is asynchronous communication, there's no need to stop and wait for some machines to perform an iterations. Actually, unless necessary. That means if we need the result of the first iteration to compute the second iteration, so in that case we have to hold the first iteration until the other computers get the result. Then they can do their computation based on the iteration 1. If not, they don't have to be wait. They can just do their iterations without any problems. That greatly reduce the delay, and it makes some optimization for machine learning tasks, which can significantly reduce network traffic and overhead also. Then the second one is flexible consistency models. Loose consistency requirements further reduce synchronization cost and delays. The parameter service allows the algorithm designer to make a trade-off between the algorithm's convergence speed and system performance based on its own situation. The third one is elastic scalability. In here, it is used a distributed hash table, which I'm going to explain later, so that new server nodes can be dynamically inserted into the collection at any time. Therefore, adding a new node does not require to restart the system. Number 4 is fault tolerance and durability. So we all know that the node failures are common. It can fail anytime, especially in the large commercial server clusters. Recovering from a non-catastrophic machine failures take actually less than 1 second. It does not require to interrupt calculations. It will just recover from the failures. And vector clocks uh, guaranteed that after recovery from the failures, it will still work well. And the last one is obviously easy to use. The global shared parameters can be presented in various forms: vectors, matrices, or corresponding space types, which greatly facilitate the development in machine learning algorithms. And the linear algebra data types provide high performance multi-threaded libraries. So that means it is very easy to use. Okay, then I'm going to move on to the parameter server system architecture. In the parameter server, each server is actually responsible only one part of the parameter. Server maintain a globally shared parameters, and each worker is only assigned to a part of the data and processing task. If you see this animation again, you can see that each child node in here, if you can see the cursor in this black color, um, child nodes only maintains its assigned parameters. You can see that after a partial update, I mean it's not going to update completely. It is a partial update, and it sends back the calculated result up to that point to the master node for global. The master node then send new parameters to the child nodes. Okay, this is how the communication between servers and workers happening. If you can see that yellow color box is the server, and these two yellow color boxes are the workers, and actually it can be up to m number of workers. I have mentioned only 2 workers here. Here the W is the working set right now, and these workers has a portion of the training data all the time. Not all the training data copied to all the workers at the same time. It has a portion of the training data. First, in the first iteration, all the workers will pull the working set from the server. That's the first iteration. Then it will compute the result inside the workers and make the answer, and then it workers will push the answers to the server. The next step, then the server will update the working set according to the answers got by workers. Again, the workers will pull the working set from the server and do their computation, and again push back to the server. Then server will update the working set again. You can see that that training data is changing from one iteration to the another iteration, like that. If you compare these 3 pictures, in the first one and the second one and third one, the training data has changing. It is actually training. This is the last iteration I'm going to mention here. It has completely trained according to the working set. Okay, this is how the communication between servers and workers happening. Here you can see the server nodes. If you can see the cursor, okay, this one. This is the server nodes. Can communicate with other server nodes. Server nodes can communicate with other server nodes. Each server is responsible for its own parameters. The server group maintains the update of all the parameters. Then the server manager in here is responsible for maintaining the consistency of some metadata, such as the status of each node or the distribution of parameters. There's no communication between worker nodes. Worker nodes always communicate with the server nodes only. In this case also, the worker nodes always communicate with their corresponding servers, not with all the servers. Each worker group has a task scheduler in here and here and here uh, that is responsible for assigning tasks to the workers and monitoring the workers' operations. When a new worker joins or exit, the task scheduler is responsible for reassigning tasks. Next, I'm gonna explain about key value pairs and range push and range pull function. In the parameter server, parameters can be represented as key value collections. The key is the feature ID and value is the weight. For space parameters, a key does not exist, but can be considered as 0 because there should be something. So representing metrics as K and V, the form is more natural, easy to reason and easier to program. Servers and workers communicate with push and pull operations. The workers send the calculated gradient to the server via push and then they update the parameters in the server through pull. In order to increase computational performance and bandwidth efficiency, parameter server allows users range push and range pull operations. If you assume that R is the range of the keys that need to push or pull, then you can do like this. If the working set is W, if you can just push the destination all the files at once, and same as the pull function also, you can pull from all the nodes at once. I'm sorry. Then the workers I'm sorry. I think I have duplicated the slide. Okay, then I'm going to move on to the asynchronous task and dependency. This is the difference between asynchronous task and synchronous task. If iteration 1 is need to be calculated after iteration 0, push and pull can only completed, then it is synchronized, otherwise it is asynchronous. That means the iteration 1 need the result from the iteration 0 to perform his task. In the asynchronous task can improve the efficiency of the system because it saves a lot of waiting process, but its disadvantage is that it is easy to reduce the it is easy to reduce the convergence rate of the algorithm. It will take more time to converge. Therefore, there is a trade-off between system performance and the algorithm conversion rate. We need to consider the sensitivity of the algorithm to perform non-uniformity, the degree of the correlation between the training data, and also the hard disk capacity. Take into the account that user will have different situations. The parameter server provides users with a variety of task dependencies. Here you can see there are three types of uh, task dependencies. The first one is the sequential. This is a synchronous task. That means the all the tasks is happening one after other. There is an order between the tasks. Only the last task is completed before the next task can be started. The second one is eventual. Uh, Compared to sequential, there is no order between all tasks, and each task is completed independently. The last one is bounded delay. This is this is an important one. There's a trade-off between sequential and trade-off between sequential and eventual dependencies. In here, you can set a maximum delay time. Assume it is as a tau, the letter tau, Greek letter. That is, all previous tasks should compute before time tau to begin the new session. So we can set some extreme conditions for this one. If tau is 0, that means the situation is sequential. If tau is infinity, that means situation is eventual. Okay, now let's look at the system running process of bounded delayed algorithm, if not proximal gradient descent, abbreviated as PGD. So in here you can see in the first part is for the scheduler, and the second part is for the workers, and the third part is for the servers. First, scheduler will iterate from 0 up to 2 and pick some random range of R and issue task to the workers. That scheduler can assign task to any worker without any ordering. He can just pick a random worker and just assign a work. In the worker set, it will wait until the iteration before T, that is a tau time, that the extreme condition I talked in the previous slide. So it should finish everything before tau time. Then compute the first order gradient and the second order gradient. Then it will push these two to the server with the KKT filter, which I'm going to explain later, and pull the new working set from the server. In the servers, it will aggregate the gradient to obtain the result from GT and UT and solve the proximal operation. So as I explained before, tau should not be much bigger, and it should not be very small also. It should be like a middle. So if I take that add click example to the account again, if you see here, the tau is the x-axis here, 0, 1, 2, 4, 8 and 16. If you can see, is the bounded delay time 8 is the best here. So it is not the 0, it is not the 1, it is not the 16 also. It's like a middle time delay is the best. Okay, next I'm gonna explain about the implementation of this. So here, if we compare two systems A and B with our parameter server, always the parameter server is the best here. Here the second one is the time, compute time. For some case, system B is better than system A because it has a best algorithm than A. But still, the parameter server time is better than both systems. In here also, the convergence time of the algorithm, the parameter server is better than other two systems. So the reasons for this is servers use the consistent hashing to store the parameters k and v value pairs, and use a chain replication to improve system fault tolerance, and also use range-based communication and range-based vector clock to optimize the system further. Okay, then I'm gonna talk about the vector clocks. Here, the parameter server use vector clock to record the timestamp of the parameters in each node, which can be used to track the status or to avoid repeated sending of data. However, if there is n nodes and m parameters, then the spatial complexity of the vector clock is n to the power m. Obviously, when there is several, I think my slide is not working. Okay. All right. Okay. Also, the parameter service using range-based push and pull to bring a benefit to parameter server. The parameters in the range share the timestamp, which obviously can greatly reduce the space complexity. So you can see in this algorithm 2 in the research paper, how to assign times to the vector clocks. In each time, a range is extracted from 3 new vector clocks, which generally in 3 devices. Assume that k is the assume that k is the range generated by the algorithm. Then the space complexity become k times m, because k is much smaller than the number of parameters, so the space complexity is greatly reduced. Then I'm gonna talk about the messages which they are passing. Obviously, the message include the key value pairs in the range and the associated vector clock with that. So it's a combination of key value pairs and the vector clock stamp. This is the equation given by the paper. So this is the most basic communication format in the parameter server. It is not only share the parameters, but but also it will format the message. Since machine learning problems usually requires high network bandwidth, there must be an information comparison. So I'll explain type of comparison available. The first one, as you can see here, is the key comparison. Comparison. Because training data is usually not changed after allocation, there is no need for workers to send the same key every time. It only need to receive the buffer when it comes the first time. Then the second time, the worker no longer need to send the key and value at the same time. It just need to send the hash of the value and key list. The instantly records the general traffic. Okay, now I'm going to explain about the user-defined filtering. So this is the one I told you before about that KKT custom filtering. In here, key comparison and value comparison can be performed at the same time. So it is like a hybrid version of those two compressions. For machine learning optimization problems, such as gradient calculate, not every gradient of the calculation is used for final optimization. The user can filter some unnecessary transmission through the custom. Um, sorry, my slider not working. Sorry. So the user can filter some unnecessary transmission through the custom rules. It will compare. It will compress the bandwidth cost more. So it is inefficient. It is inefficient to send the small gradient value. So you can customize the settings and send only when the gradient value is a little bit high, little bit larger. Then the updating the value close to the optimal situation is also inefficient. So values like this can be judged by the KKT custom filter. Next, I'm gonna discuss about replication and consistency. Parameter service using the consistent hashing in traditionally the parameter key and server node ID are inserted into the hash ring, like in this picture. So the specific consistency hash algorithm is not the focus of this article. The main focus of this article is parameter server. So as long as it is known that its role in the distributed system, dynamically adding and dynamically removing node can also ensure the performance efficiency of system storage and key allocation. Then I'm going to talk about these replication methods available. Sorry, actually I forgot to tell you something here. Okay, in this keyring, k is 2. That means every data has 2 copies. So the when server 1 replicate the key range owned by the server 2 and server 3. So here there is a two-way to ensure data consistency between slave and the master. Okay, so now I'm going to move to the replication method which are available. So the default replication method is a chain replication. It is so reliable and it has a strong consistency. So you can see in this picture, the update can only occur in the data head node, and then update the gradual move until the update reach the tail node, and the tail node confirms the update success to the customer. In order to ensure a strong consistency, the customer query can also be at the end node. Okay, then the second one is the replication after aggregation. The two worker node respectively transmit X and Y to the server. Server first can think like different way. It will think like it is a function of X plus Y, like that. So if you can see here, the worker worker 0 push Y and worker 1 push X. So the server will aggregate these two and copy the operations. When there are n copying workers, copying only requires k divide n bandwidth. In general, k, which is a number of copies, is a small constant, and the value n is probably a few hundred to few thousand. Okay, next I'm gonna talk about the server management. To achieve a system fault tolerance and dynamic scaling, the system the system must be able to support the dynamic adding and removal of the nodes. So what happens when there's a server node added? First, the server manager will assign some range key to the new nodes, uh, which will cause changes to the key of the other server nodes. Then the server node will obtain the data for the training purposes. Then finally, the server manager will broadcast the changes of the node. Receivers may receive data that is no longer theirs and submit unfinished tasks to the node. Then the next one is what happens when there is a worker node added. So it is also similar to the server. It is relatively simply. First, the task scheduler will allocate data for W. That means the working cell. Worker node. Then the worker node get assigned training data via the network or file system. Then W will pull parameters from the server. Finally, the task scheduler will broadcast the changes of the node. May take some node release a part of the training data. And finally, I'm gonna summarize which I talked up to now. So first, we start describing a parameter server framework to solve distributed machine learning problems. This framework is definitely easy to use, and it is efficient. All communications is asynchronous, and it is a flexible consistency model supporting the balance, the trade-off between system efficiency and fast algorithm convergence rate. Also, it provides elastic scalability and the fault tolerance. Finally, we show some experiment like that at click example for several challenging tasks on the real data set, which has billions of variables, and demonstrate its efficiency. These are the references I used to make this video. The first one is the original research paper, and the second one is the website that we can download the code of the parameter server. And third, fourth, fifth, and sixth are some links which I used to learn about this parameter server and distributed machine learning system. Okay, thank you so much for listening. If you have any questions, please comment below. I will answer them as soon as possible. Thank you so much.